Hello there, welcome back. Today we are talking about capacitors. In fact, this is how we're going to spend the next two lessons in this unit. Capacitors are going to build on what we already know about circuits, but they're also going to kind of challenge our thinking about a few things because while they are going to follow a lot of the same rules we've learned about for circuits and resistors and all that sort of stuff, we'll see they're also kind of unique in their own way. So to start off with, what is a capacitor? So a capacitor just consists of basically two parallel plates of conductors. So two parallel conducting plates that are separated by some sort of insulating dielectric. So you can see here in my picture, this is what it looks like. I've got two conductor plates on top with a dielectric in between. A dielectric is just any material that's going to separate those two plates. So one way to visualize what's happening here is if I have a capacitor like these two plates here, I could connect them to a power source. And when I connect them to a power source like this, what's going to happen is if the power source has a certain voltage, say 1.5 volts, what's going to happen is we're going to build up a charge on these plates. Now, it's important to think about why this happens. So we end up building a charge on this plate, and then we can actually disconnect that from the battery, and you notice that the charge stays put. So we've got this charge distribution, there's nowhere for them to go. So we've essentially stored up a whole bunch of charge. And if we're storing a bunch of charge, then we're also storing a potential difference, which means we're storing energy. I could, for example, take this capacitor and connect it to another circuit, and that would then release that charge, would release that energy, electricity would flow back the other way, and I would get it in a way that's different from a battery. Whereas batteries tend to have internal resistance just built right into them, this capacitor doesn't. And so I can actually deliver a pretty high a pretty high current in a really short amount of time. And that's kind of why capacitors, well, one of the reasons capacitors are useful. So I'm just going to go back and charge this capacitor up again, and let's think about what's actually happening when we charge a capacitor. When I connect this to the battery, the second I do, and it happens pretty quickly, but the second I do, electricity starts to flow from the battery. Now we know there's conventional current and electron flow, but I'm going to talk about electrons actually flowing here because that's what really happens. You can see what's going to happen is electrons are going to flow from the negative terminal of this battery. And the reason they're going to do that is because this bottom plate initially is uncharged, it's neutral. And electrons, because they're being pushed by the voltage of the battery, are going to want to move, and so they do. And the first electron to show up in this plate thinks this is a pretty good deal because that plate is neutral. There are protons and electrons there, but there's no extra electrons. So the first electron that shows up is going to think this is a great place to be. And then the second and the third and the fourth and the fifth and eventually the 100th and the 1000th and the millionth and the billionth electrons start to show up. And there's more and more electrons piling onto this plate. Well, we know that electrons don't like other electrons. They're going to repel each other. Eventually, we're going to get to a point where so many electrons build up on this bottom plate that no more electrons can fit. Essentially, what happens is, even though the battery is pushing with a certain amount of voltage, there's like a back pressure created by all the built up electrons on the plate that's pushing back against the battery, which essentially prevents the flow from continuing. Now, that's actually kind of half the story because while you see the bottom of the plate is negatively charged, the top of the plate also becomes positively charged, and that's an important part. So why is that? Well, we can see here that I'm going to create an electric field, right? This bottom plate, which is negatively charged, is going to create an electric field. And that electric field is going to travel through empty space and is going to be felt by the top plate. And essentially, those electrons that are building up on the bottom plate are going to repel electrons from the top plate. So the electrons on the top plate, again, the top plate starts as neutral, but the electrons on that top plate are going to sense the electrons below them, and they're just going to get on out of there. Where are they going to go? Well, they're going to flow back to the battery. In actual fact, what ends up happening is the amount of charge that flows onto the bottom plate actually is equivalent to the amount of charge that flows off of the top plate and back to the battery. So we get a charge distribution here that really just depends on the voltage. And you can imagine here that this charge is going to flow until we reach a steady state. And the steady state happens when the voltage itself matches the voltage of the battery. So we're gonna pack charges on there, but at a certain point, we're not going to be able to pack any more charges. And that's essentially how a capacitor works. So let's just jump back to here. So I should say in that little simulation here, we didn't see a dielectric, but the dielectric can be made of any sort of material that doesn't conduct. And the reason it's there is simply to prevent the electrons from jumping across the plate. If you had a really terrible dielectric, like something that was semi-conductive, then at a certain point electrons would just start jumping across. At a certain voltage they'd be like, let's just go for it. You could just use air. Air is a pretty good insulator, or you could use something that maybe is actually a little bit better of an insulator, and not only better of an insulator but also conducts the electric fields better than air does, and we'll talk about that in a bit. So really what makes capacitors useful is their ability to store charge. And if they're storing charges, then they must also be storing a potential difference. And this potential difference can be used, for example, to do things like create uniform fields, like we learned about in the last unit, or store energy for some later purpose. Okay, the capacitors are used in all kinds of things. One example is as an energy storage device, but they're also used in things like with alternating current and to prevent spikes in voltage, and that's something that you'll maybe learn a little bit later on. But just know that they are basically ubiquitous in modern electronics. Now, the symbol for the circuit symbol, I should say, for capacitors, and I do apologize for this, but it kind of looks like this: two parallel bars side by side. Now, this is not to be confused with this symbol, which of course is way different, and you can definitely tell the difference there. That symbol there is a battery, or a cell, I should say, and this symbol is clearly a capacitor because the two lines are equal in length. So the capacitance of the capacitor basically tells us, it gives us a sense of its ability to store charge. You can almost think of a capacitor as like a reservoir of electrons, like a bucket of electrons that we can use to push through a circuit somewhere. And so the capacitance kind of tells you how big the bucket is. It really tells you the amount of charge for each volt applied, because as you can imagine, that capacitor we saw in the simulation, we charged it up until it got to an equivalent voltage of the battery. Well, if I cranked up the battery to 6 or 9 or 20 volts, I would be packing more and more charge onto my capacitor. Now, the unit for capacitance is called the farad. Okay, and the farad is going to be abbreviated as capital F. And just something for you to know so that you kind of get used to it is that 1 farad is actually a huge amount of capacitance. Most capacitors are going to be in the milli or the micro or the nano or even the pico range. So most capacitors are going to be much, much smaller than one farad. Now, let's think about what factors are going to affect how good or how strong or how large the capacitance is for a capacitor. I'm just going to jump back to the simulation to think about this here. So one of the things I could change about this capacitor, for example, is I could change the size of the plates. So I could make the plates larger or smaller. And what you might notice is as I make the plates larger, we can see kind of at the top here, the capacitance. As I make the plates larger, the capacitance increases. And as I make the plates smaller, the capacitance decreases. Now, hopefully this kind of makes sense based on what we've been talking about so far. If we think about these plates as just a region that electrons can start to gather on, well, the bigger the region is, then the more electrons we can pack into this place. I think about this a little bit like going to the beach, right? You can only fit so many people on the beach until they're like side by side by side. But if you had a bigger beach, I guess you could fit more people, right? So the larger the surface area of the plates, the greater the capacitance. But the other thing we can change is we can change the separation of the plates. So I could actually move these plates further apart. And this might not be quite as obvious why this happens, but the closer the plates are together, the greater the capacitance is, and the further apart they are, the less it is. The reason for this is fairly simple. Notice that the electric field between the plates also gets much stronger as they get closer together. That's just basically saying that when the plates are close together, the top plate can really sense the electrons building up on the bottom plate. Well, what that means is the closer they are, the stronger the field, the more the electrons from the top plate are going to want to go and move away from the bottom plate. But that has a feedback effect, because if I remove more electrons from the top plate and it becomes more positive, then that makes the bottom plate even more attractive to more electrons. So as more electrons leave the top plate, more and more electrons will join on the bottom plate, and so on. Of course, it still reaches a limit, right? There's some maximum amount of electrons we can pack onto this capacitor. So what we say is the capacitance of the capacitor, C, is equal to E naught kappa A over D. Now, two of those things you're well aware of. A is, well, three things, I guess. C is the capacitance, okay, measured in farads, and A is the surface area. And for our purposes, so far anyways, we're going to have plates that have equal surface areas. That'd be mean if they had different ones. Remember that surface area has to be in square meters. And then D is just the separation of the plates. And again, separation has to be measured in meters, but that's going to be a very, very small number of meters. Now, the last two things I just want to point out here is E naught and cap. So E naught is it's a constant, and it's known as the permittivity of free space or of a vacuum. And that's not a very satisfying definition, but it has a value of 8.85 times 10 to the negative 12, actually. Now, what does it mean? Well, basically what it means is the permittivity of free space gives us an idea of how difficult it is for electric field lines, how difficult it is for electric field lines to move through space. So essentially what we're saying is that in our universe, if field lines, like anything else, if they want to move through space, it's going to have a certain amount of, it's going to be either easy or hard to do. And in our universe, this gives us a measurement of how difficult it is for the field lines to move through just plain empty space. Now, those field lines can have an easier or harder time depending on what they're trying to move through. Through a vacuum, it's 8.85 times 10 to the negative 12. But through other materials, like maybe an iron bar or something else, it's going to be very different. And that's where kappa comes in. And kappa is basically just the permittivity of the dielectric. Now, which is approximately equal to 1 for air. So if we're talking about air or just an empty vacuum, then kappa just goes to 1, which makes sense because then it's just the permittivity of free space. But for any other material, it's going to have some number. Now, typically, I don't think you're going to find too many questions around this. The key thing to recognize is the effects that area and separation have on our overall capacitance for our capacitor. So we'll do a quick question here. It says the plates of a parallel plate capacitor are circular, the radius of 6 centimeters each. Notice centimeters. The separation between the plates is 2 centimeters. Determine the capacitance if the material between the plates has a dielectric constant of 1, which means it's not a very good dielectric. So the capacitance would just be equal to E naught kappa times area over the separation. So 8.85 times 10 to the negative 12. And in this case, kappa is just 1. Times the area. Now there's circular plates, and we know the radius, so that's going to be times pi r squared. The radius is 6 centimeters, so 0.060 squared, all divided by a separation of 0.02 centimeters. And when we work this out, it's pretty small. It's like 5.0 times 10 to the negative 12 farads, which, as it turns out, would be right around 5.0 picofarads, which again is very, very small. Okay. So good stuff. We kind of know how capacitors are made and how they and what affects their capacitance. Let's just talk a little bit about what's what's going on when we actually connect them. So when electrons flow into the capacitor, like we said, they kind of get stuck. And I'll use that term stuck because there's nowhere else for them to go, and they can't jump through the dielectric. So it's really important that as the electrons pile onto the oncoming plate, it has an overall negative charge, and this makes sense. And then this buildup of negative charge does influence the positive plate, which causes them to move away, giving them an overall positive charge. Okay. Now, at some point, like we saw in the simulation there, at some point the capacitor gets full, which is to say that at a certain point, the voltage we're providing is only going to pack so many electrons into that space. And so once it's full of charges, they cannot move. Okay, so this is where capacitance comes in, because this tells us the amount of charge per unit of voltage. Okay, so to put it in a nice handy equation, like we're going to right here, we could say that the capacitance is really just a measure of the amount of charge built up per unit of voltage, where again C is my capacitance, charge, Q is my charge, and V is my voltage. Okay, so if we look at an example, or a potential difference, I guess, for voltage. If we look at an example, a student pushes the shutter button on their camera, the flash unit releases this much charge that was stored on a 0.5 microfarad capacitor. What is the potential difference across the plates inside? So we know that C is equal to Q over V, so then V must be equal to Q over C. We released 4.5 millicoulombs of charge, so times 10 to the negative 3 coulombs, and it is a 0.50 microfarad capacitor, so that's times 10 to the negative 6. And so overall, this is going to give me, the voltage must have been 9,000 volts. It seems like a large voltage for the flash of a camera, but who am I to judge? Okay, I want to just kind of recap quickly here and think about a few things, because obviously now that we have learned about capacitors, we're going to start attaching them in all sorts of fun and unusual ways, like series and parallel. So one capacitor on its own, pretty straightforward, but what's going to happen when we connect these things in series and parallel? So let's think about the capacitance. Okay, so what is going to happen to the total capacitance of a circuit when it's in series, and the total capacitance of the circuit when it's in parallel? Okay, so as a reminder, if I create maybe I have a battery, and I create 2 capacitors in series, and then over here I've got maybe some battery, and I've got 1 capacitor and 2 capacitors side by side in parallel. Now, just for the purposes of this thought experiment, let's just imagine all the capacitors have the same value, although the rules will still hold even if they don't. So the first thing I'm actually going to think about is actually over here in parallel. This is, to me, a little bit easier to think about it in parallel. If I just had the 1 capacitor on its own, obviously I would have a capacitance just kind of equal to C1. When I come along and add a second capacitor, in a way what I've done is I've kind of increased the total area available for electrons to gather on. In a way, if you go back to this formula up here, it talks about capacitance, I've essentially increased the value of A. I've created more area to jump onto, which means I've increased the total capacitance of this circuit. So in parallel, my total capacitance is going to be the sum of the individual capacitances, which is just like saying it's just like C1 plus C2 and on for however many capacitors I have. But what about in series? Well, in series, when I add a capacitor and then I add another one after it, the electrons are going to come out of the battery, they're going to flow to the first plate, and they're going to push those electrons off the next plate, and they're going to go to the next capacitor and so on. But essentially what I've done in a way is if you look at this gap right here, I've increased the separation between plates. There are now more gaps that the electric fields have to push across in order to convince electrons to move. And if you think back to this equation from the beginning, if I increase the value of D, if I increase the separation, then I'm actually decreasing the effective capacitance of my circuit. And so in actual fact, what we see here is that 1 over the total capacitance is equal to 1 over C1 plus 1 over C2 and so on. So adding capacitors in series decreases the capacitance, and adding capacitors in parallel increases the capacitance. Notice that that is exactly the opposite of what we had for our resistors. But now let's think about voltage. So what is going to happen with my voltage? And for my total voltage, for example, like I would measure the total voltage here at the battery in each case. So I'm going to measure total voltage here, okay? And then the individual voltages at the individual capacitors. So I'm going to measure like V1 here, for example, and V2 I'll measure, boop, if I just fit there, okay? And then for my voltage, in this case, I might measure voltage 2 here. I'm not going to draw voltmeter 1 because it's getting pretty busy, but you get the idea. So in this case, let's think about the parallel situation first. I think it's a little bit simpler. You can see that actually, since the capacitors are connected in parallel, if I was to cut that circuit, if I was to cut off capacitor 2, capacitor 1 wouldn't even know that had happened. The voltage that capacitor 1 is going to receive is going to be the entire voltage of the battery. So essentially, the voltage at the battery is going to be felt by capacitor 1, and the same thing for capacitor 2. So each component in parallel will receive the same voltage. Now over on the series side, you can see that I have to use a certain amount of voltage on the first capacitor and a certain amount of voltage on the second capacitor, which means they're going to add up to the total capacitance. So this is going to look like the sum, which is really the same as V1 plus V2 and so on. Now notice that these rules for voltage, these rules are the same as they were for resistors, right? Because of what we saw before with like Kirchhoff's laws. And the last thing I want you to think about is charge. So let's talk about total charge. Now, when I talk about total charge, we have to be kind of careful here because a circuit is a closed system, right? Like the charges aren't entering or exiting the circuit. And so the total charge in the circuit is going to have to stay constant. And that's Kirchhoff's junction rule. That's Kirchhoff's current rule that says, look, whatever flows in to a point has to flow back out. But when I say total charge, what I'm saying is, let's think about the total charge that flows out of the battery right here. So I'm thinking about QT as like the total charge that flows out of the battery in each case. Okay, so that's the charge there. Now, again, if we look at parallel, you can see what's going to happen here is the total amount of charge is going to flow out of the battery, and then it is going to split, much like current, right? Is going to split between these two. And so the total the total charge that flows is going to equal, it's going to equal the sum. It's going to equal the sum of the individual charges on the individual plates, which is to say Q1 plus Q2 and so on. But what about for series? Well, whatever amount of charge flows off out of that battery, all is going to collect on the first plate, which is then going to cause the capacitor to push that same amount of charge to the next plate, which is going to cause the same amount of charge to flow back to the battery. Notice that in each case, the total charge that flows back to the battery has to be the same as what flowed out of it, because again, it's a complete circuit. And so in this case, the total charge here is just going to equal the charge that builds up on the first one, which is going to equal the charge that builds up on the second one. And can't stress this enough, but the charge on the plates is referring to the charge on either one of the plates. If you measure the charge of the top and the bottom plate, overall it's going to be neutral, but we're just talking about how much charge has been built up on the one. Okay, so this is a lot, but let's try and use all of this to solve a problem, a little more complex capacitor problem. Okay, so what we've got here is they're looking for the total capacitance of the circuit and the charge that's going to build up on each of these capacitors once we plug it into this battery. Okay. Now, just a reminder here that the EMF here of the battery really just refers to the total voltage that the battery can supply, and you can see there's no resistors in this circuit, so we're not going to worry about that yet. Okay, so the total capacitance of the circuit. Well, I've got. I could think of this circuit here. I could think of this really as being like a 12-volt battery connected to a first capacitor. I'll call it C1. And then this whole parallel situation, I'm going to think about that as being a single capacitor with a value of Cp. So C1 has a value of 3 microfarads. And we can see that C2 and C3, since they're in parallel with each other, are going to have a total effective capacitance of 6 microfarads, right? Because they're just going to add up because they're in parallel. So the total equivalent capacitance is essentially going to be the total capacitance. I'm going to use my capacitor rule for series, which is to say that that's C1 to the negative 1 plus Cp to the negative 1 all to the negative 1. So I've got 3 to the negative 1 plus 6 to the negative 1. So my total overall capacitance is 2 microfarads. Sorry, I cheated and didn't put my micros in the number there, but I think we get it. So the total capacitance of the whole thing is 2 microfarads. Great. But now I need to find the charge at each capacitor. Well, the first thing I could do is I could find just the total charge. So we know, for example, that capacitance equals charge divided by voltage. And just like we saw with Ohm's law, I can use this for the whole circuit, or I can use it for just one part of the circuit. And so I could say that like C total equals Q total times V total, which is to say that the charge, the total charge that flows, which is to say that the total charge that flows from the battery is going to equal C total times V total, which is a capacitance of, what we said, 2 microfarads. I'll put my micro in this time so I don't get in trouble. And then the voltage is 12 volts. And so this is going to have a total charge of 24 microcoulombs is going to flow from the battery. Okay, so 24 microcoulombs go out that way. And then 24 microcoulombs come back too, right? So it's got to be complete, a complete circuit. I'm going to find the charge on C1 first because C1 is in series with everything else. If 24 microcoulombs flows out of the battery and then splits and does I don't know what, it's got to come back together to meet on C1. So Q1 is just going to equal Q total, which is just going to equal 24 microcoulombs. So that's one of my answers right there. But now what about C2 and C3? Well, there's a couple ways you could do this. You could reason it out proportionally, but I'm going to take a slightly longer route because I think it makes it more explicit, which is to just kind of solve for what's going on here. I know Q1 at this point. So I'm just going to put in here, I know Q1 is equal to 24 microcoulombs. And just like we kind of saw when solving circuits, if I know two things about that capacitor, I can go ahead and find the third thing, right? So since I know that the capacitance equals charge over voltage, I know that the voltage, V1, is going to equal the charge divided by the capacitance. So that's going to be 24 microcoulombs divided by 3 microfarads, which means this capacitor right here is going to use 8 volts. If I'm using up 8 volts on this C1, then I must have 4 volts left over for my C parallel. So just to kind of point this out, I've got my voltmeter here, and this is measuring 8 volts. So then at this voltmeter, I must have 4 more volts to spend. And that means that both C2 and C3 must get the same voltage. So this is 4 volts for each of these. So V2 and V3 equals 4 volts, which means, long story short, I can calculate Q because, again, Q is going to be, Q2 is going to equal C2 V2, which is going to equal a capacitance of 5 times, 5 microfarads times 4 volts gives me 20 microcoulombs. And then Q3 is going to equal C3V3. So that is going to equal 1 microfarad times 4 volts. And what do you know? I get 4 microcoulombs. Okay. And last thing I'm just going to point out about this is, as it turns out, look, it added up to my same 24 microcoulombs that I expected. So you could have worked it out proportionally, but that's maybe something you can try on your own. Okay, that was a lot about capacitors, but we're all done. Okay, good job.